Okay, our speaker, Alex Condello, is the Director of Algorithms, Performance, and Tools at D-Wave. His responsibilities include the Ocean Quantum Software Development Kit, D-Wave suites of quantum tools, benchmarking, and the development of hybrid algorithms that combine classical and quantum resources, such as what he'll be describing today. Alex is also heavily involved with many of our customers in our professional services team. Alex earned a Master's of Applied Science in Mathematics from Queen's University in Canada. So welcome, Alex.
Awesome. Thanks, Susan. Hey, everyone. Really excited to be here to talk to you about some of our new features in our hybrid solvers. So as Susan mentioned, one of the things that I'm responsible for here at D-Wave are these hybrid solvers. These are ones that combine classical and quantum resources together to get the best of both worlds. And we have some new features that have come out of them over the last few months. And so I wanted to take the opportunity to tell you all about them and sort of give you a sense of what it looks like to use them. Before I get too far down that path, though, I want to start off with a little bit of context. I think everybody here knows, but it's worth repeating, that D-Wave is a comprehensive full-stack commercial quantum platform. So what that means in practical terms is that we are laser focused on solving practical problems for you, the customer, using our hybrid products and our quantum computer. So if you wanted to be a comprehensive full stack commercial quantum platform, you would need a couple things, a couple ingredients to make that work. So the first thing that you need, and it's first and probably the most important, is the quantum computer itself. And right now at D-Wave, our flagship quantum computer is our Advantage 5000 qubit system. Just having a quantum computer, though, by itself is not actually all that useful because you need access to it. You need an ability to get it to you, the customer. And for that, we have Leap, which is our cloud service platform. And in fact, most of the demos I'm going to be doing today are in Leap. So almost everything I'm going to be doing, actually pretty much everything I'm going to be doing, is live. And all of it is going to be taking place in our Leap platform. So Leap gets you access to our hybrid solvers and our quantum computer. So you also need something on your own system to sort of talk to Leap. And for that, we have Ocean. Ocean is our set of open source tools for constructing problems that can be solved by the quantum computer and the hybrid solvers. And it's available in open source. You can see exactly how it works. You can take it apart. You can make pull requests or feature requests or changes that you like. To sort of customize it to your needs or to give us feedback or to improve it for the ecosystem as a whole. And the last thing you might need is a little bit of help getting started. So for some folks, maybe they feel ready to just jump into solving problems, but for some folks, maybe they want a little bit of help, distilling their problems from a business question into a mathematical model that can then be solved by our products. And for that, we have our launch program, where we work with individual customers or individual groups to help them formulate their problem for quantum computing and get sort of the most benefit they can out of our hybrid solvers. So today, though, I'm going to be mostly focused in on those hybrid solvers. And I've used that phrase a couple times, and Susan and I both defined it, but I'm actually going to define it one more time because it's so important. Hybrid solvers are solvers that combine both classical and quantum resources together to solve problems. So you're getting the best of both worlds. In Leap right now, we have 3 hybrid solvers available to you that you could get started with right now. The first, and often the one that people gravitate towards first, is our constrained quadratic model solver. So I'm actually going to take a moment later to describe what a constrained quadratic model solver is, but I'll introduce it very quickly now to just say that this is the solver that solves problems with constraints. It's sort of right there in the name. And that's important because business problems have constraints. Often you are doing things subject to constraints. I want to deliver all of these goods subject to certain cost constraints, or I need to deliver at least this many things to the customer, or have this many days of redundancy in my logistics pipeline. All of those are constraints on the different solutions. It's not just it's not just problem solving where all you need to do is find the best answer. You need to find the best answer within the realm of feasibility. There are 2 other hybrid solvers in our platform. We have a binary quadratic model solver and a discrete quadratic model solver. And what I will say about those is that each of these represents a different mathematical problem class. And using, depending on what class your problem is, you would use the correct solver. So a binary quadratic model solver involves binary variables. Those are yes, no, red, blue, 0, 1. And discrete quadratic model solver uses categorical variables. So that would be like red, blue, yellow, green. You have one of 4 choices, or I want to use the truck or the airplane or the train. Those are categorical variables. And then the constrained quadratic model includes all of that plus constraints. So it's in some sense the most general model. So honing in then on these constrained quadratic models a little bit more, I think that the phrase I want you to have in mind when you think about these constrained quadratic models is that you want to minimize an objective subject to constraints. So to give you some examples of like what that actually looks like practically is I want to minimize or use as few trucks as possible subject to having enough total capacity to deliver my goods. Or maybe subject to my drivers not working more than 8 hours because they have union rules. Or maybe it's subject to keeping my repair costs on my fleet low. Another example might be, I want to minimize the total risk in a financial portfolio subject to a certain target revenue or a certain target gains. Again, all of these sorts of problems and many, many problems in business sort of take this form. I want to find the best solution, minimize an objective or cost, subject to certain restrictions on my solution space. There is a mathematical description of this for those of you who are interested. So specifically, our objective will be a quadratic cost function so over variables that are either binary, integer, or continuous. And our constraints are also quadratic equations where there is a less than or equal to, a greater than or equal to, or an equality relationship to a right-hand side. So, if anybody's interested in the sort of mathematical aspect of that, I would definitely encourage you to check out our docs. We have lots of descriptions about this. But for this presentation, I don't think you really need to understand the math on a deep level. You just need to understand this idea of minimizing objective subject to constraints. So actually, it turns out that many, many, many problems fall into that category. And if we started to take this sort of notion of binary and integer and a mixed integer, which is to say, including continuous variables, you can create this sort of hierarchy of problems, different problems that fall into different areas of this overall region. And so that includes things like bin packing. So, you might want to be packing as many boxes as possible into a shipping container. Or electrical grid optimization. I want to make sure that I have enough power so that if there are surges in demand, I'm able to meet those surges. Or graph coloring. I want to color my map of the United States, or maybe I want to make sure that I have each individual cell tower isn't interfering with adjacent cell towers. Lots and lots of different problems sort of fall somewhere within this space. And our constrained quadratic model solver sort of hits this whole space, which is what gives it its power, and which is why that's the solver that most people, when they want to get started on our systems, they start with that constrained quadratic model solver. Okay, so up till now, everything I've been talking about has been prelude. I've been talking about our constrained quadratic model solver sort of in general terms, our hybrid platform, and Leap, and all of that. So now, though, I want to focus in on the new things, the shiny new stuff that has come into our platform over the last few months. And the first one is this notion of weighted constraints. So rather than sort of read the slide and tell you about it, I'm actually going to show you a live demo of what this looks like to use, because I think that'll actually help demonstrate this power a lot more. So I'm going to stop sharing this real quick. And share this one. Oh, and move this. Okay, so I'm going to start this demo in the same place that I like to start all my demos, which is right here in Leap. So I mentioned earlier, Leap is our cloud platform. By the way, you can sign up to Leap for free. You could do, if you don't have an account, you could go get one right now. And everything that I'm doing today is live and in Leap. So you could actually, click for click, follow along everything that I'm doing, and see it for yourself, experiment with it, try some stuff that I'm not doing, explore and understand to help build your understanding. You're also welcome to watch me do it. So Leap has a lot of great stuff. You can see what set of quantum computers and hybrid solvers you have available. You can see problems that you've submitted. You can see that you'll see in a moment that I've been practicing this demo because you'll recognize that name. So lots and lots of different great resources that you could check out. But today I'm going to be focusing in on one specific set of resources that I think is really powerful. And that is our set of open source examples showing how to solve practical problems. For the most part, there's some fun ones like Sudoku, using our hybrid solvers or our quantum computer. And each of these is an open source example that you can take a look at exactly how we formulated the problem and how we use the hybrid solver or the quantum computer to solve it. I'm going to focus in on one specifically, which is this Tor planning, because that's the one that makes use of the new weighted constraints feature that I want to be talking about today. So I'm actually going to open up this example in our integrated developer environment available in Leap. This is an online IDE for developing quantum applications. It has everything that you need to get started on building a quantum application sort of in one place in Leap. So you don't have to install anything. You don't have to do anything other than sign into Leap and open up this IDE. So what's happening under the hood right now is that it's actually pulling that open source example and it's installing everything that it needs in order to get running. So it's just going to take an extra couple seconds to get going, and then we'll be able to start our demo. As I said, this is this full featured environment. Oh, there's the demo. This is this full featured environment. It has sort of Python files and all the sort of assets. So you can really understand exactly what we're doing under the hood of this sort of more polished demo I'm going to be showing. But let's jump over to that more polished demo. Okay, so here's the problem I want to solve for now. Let's say that you are on vacation. You're out in the world, and you wake up one day. You have a day ahead of you, or maybe a couple days, and you decide that you want this to be a virtuous vacation. You're going to get some exercise. And luckily, it just so happens that nearby there is a road or maybe a loop that has several different road sections of different grade. So the colors here, the lengths of each of these blocks represents how long the section is. So overall, this looks like about 65 miles. I guess we'll use miles instead of kilometers because, why not?
Alex, can you just make the screen a little bigger so people can see it?
Bigger.
Is that doable?
How's that? It's about as big as I can make it.
Much better, yes. It's hard on small screens.
Yep, no problem. Thank you. So I have, so overall, this road is about 65 miles long, maybe more like 66. And each of the different sections has a different grade to it. So there's different slopes. So the more orange it is, the steeper it is, and the more blue it is, the flatter it is. And I guess this is the road that my grandfather built because it's all uphill. No matter what, I can't go downhill ever. In principle, it's easy to define downhill. It just makes the demo a little smoother to show only uphill. And so, because I'm on vacation and I have a fixed amount of time, I have a budget, and that budget is in terms of cost and time. So cost will be, the amount of dollars, say, that I have available, and time is, say, the number of hours that I want to dedicate to this. Now, at each of these different road sections at the beginning, there is a helpful little place that will rent me vehicles. So for each road section, I have 4 options. I can walk, I can cycle, I can take the bus, or I could drive. And each of these different options has trade-offs. So walking is obviously the slowest relative to cycling, relative to bus, relative to driving, but it's also the cheapest. So walking is free. Renting a bike will cost me $2, a bus will cost me $3, and renting a car will cost me $5. Similarly, they give different levels of exercise. Cycling gives me a bit more exercise than walking, but a bus or a car doesn't give me any exercise at all. And so the goal here, to use the language from before, is I want to maximize my exercise subject to my cost and budget, or my time and budget constraints. So one of these constrained quadratic models that I was describing before. So let's say I have $156 in my pocket and I have 16 hours, and let's go ahead and give this a run. So right now, this is running on our hybrid solver live. So it just got submitted to one of those solvers that combine classical and quantum resources, and everything I'm doing here is live. It made use of that solver called the quantum computer, all in real time. And what I see here is that actually I wasn't able to find a solution. There is no way to traverse this entire road subject to my cost and time constraints. So that's okay. I can sort of bump those up a little bit. I can give myself maybe $200 and maybe I'll give myself 20 hours and let's give that a go and see how that goes. By the way, I will mention that this route is randomly generated every time you open the demo. So if you're following along with me, it might look a little bit different. And that's also why I don't actually know in advance what the right answer is. I don't actually know what will work, but it looks like my budget of $200 and 20 hours did in fact work. And I can see that my optimal solution is to cycle several paths, to drive for some of the steep ones, take a bus here at the end, and that will give me my maximum exercise subject to my constraints. I can actually get a nice sort of visual representation of this by looking at this feasibility space. So I can see that I got 286 units of exercise, that my time was just about 19 hours, and that my cost was around $165. And if I sort of mouse over this, I can sort of get all of that specifically. Okay, so one of the things you might be asking though is like, what if I do have a harder constraint? Like what if I can't just loosen my budget like that. I need to understand what actually it looks like to solve this problem in that infeasible region, in that space where I can't just sort of up my budget. So let's go back down to that original number. So let's go back down to $160 and maybe 15 hours. I think those were the originals, but if it weren't, it's close enough. And now I'm going to start using my so-called soft constraints. So the idea is that a soft constraint is a constraint that is allowed to be violated. Soft constraint, by the way, is the same thing as a weighted constraint, which is this new feature. So the weighting is the amount I care about that constraint, and a soft constraint is a general term for a constraint that can be violated. So by using these soft constraints, I can say that my time budget is hard. I have 15 hours, or actually, let's say my cost budget is hard. I have $160 and that's all there is to it. But my time budget is soft. I'm willing to go a little bit over that 15 hours. And so if I try to solve this problem, what I will see, and again, this is running live, so it takes a couple seconds, is that I can find a feasible solution to it. And that feasible solution will respect my cost constraint, but it might not necessarily respect my time. So if I take a look at it, I can see that I got a cost of $159.70. So it did respect my cost. But unfortunately, my time was a little bit over. It was over, I took 19 and a half hours rather than 15. Similarly, I could set my time constraint as the one that I care about and loosen my constraint on the budget. And so if I do that same thing, again, it's going to submit, it'll take about 6 seconds to run. I get a different answer. In this case, it looks like I'm mostly driving and mostly taking the bus, which is faster. So ultimately, I get my time constraint, but I get my time, which is just about 15 hours, but I don't get my cost. I overran. So you can kind of see how this ability to soften constraints gives you a certain amount of flexibility to express your problem. The real power of this comes in, though, when I set them both soft. And this is where this notion of weighting comes in. So weights are the amount that I care about each constraint. So here I'm saying that both my time and my cost are negotiable, but that my cost is more important. I'm giving that a weight of 100 relative to the time. So my time, I'm saying I'm much more willing to give up some of my time than I am my cost. So when I run this problem, and this will be the last one I run for now, what I should see is that probably it will violate both, but it will focus more on saving me money than it will on saving me time. And you can see that that's in fact what happens. So I'm spending, when I am using fast vehicles, I'm using buses, which are cheap, and for the rest of the time, I'm cycling. So it's sort of giving me that sort of ability to manipulate the trade-offs between those two constraints when I'm in this regime where I can't satisfy both. Okay, so I'm going to stop sharing that for a moment and return to my slides. So just to sort of sum up this notion of weighted constraints, the primary benefit this gives you is a more accurate problem formulation. And what I mean by that is that often when I'm actually trying to solve practical problems, some of my constraints, not all of them, but some of my constraints are negotiable. Maybe that 8-hour constraint on my truck drivers I mentioned earlier is negotiable. I can have them work overtime. There's just a cost associated with that. And so I can more accurately represent my problem by including this notion of weighted constraints in the formulation. Whereas before, I had to just say, no, they can't work 8 hours, and that's not actually true. I do have a little bit of wiggle room in some cases. This also expands the set of problem classes that you can solve. So there are some problem classes that just straight up rely on the existence of soft constraints. So one example of that might be circuit fault diagnosis. So I want to understand, I see that my system is giving me bad readings and I want to understand where something went wrong. That actually uses this notion of soft constraints in order to solve it, because you basically say that each component in my system is constrained to work correctly, but it's soft, they can break. And so I can use this to sort of understand what might have broken in order to induce the broken output. And then ultimately, what this gives us is the same thing that all of our features are attempting to give us, which is better time to solution. That is to say, by representing your problem more accurately, you can get better results. So you can get either better results for your time budget, or you can get the same quality results in less time. Either of those are two sides of the same coin. Both of them are obviously the main goal of most businesses is to get something as cheaply as possible. Okay, so that's the first of the new features. The second one that I want to talk about then, changing gears, is pre-solve techniques. And just like before, rather than show this to you in slide form, I'm actually going to jump back into Leap. So switching back. So in this case, rather than showing you a demo in sort of a GUI demo that uses that sort of Dash platform, I'm going to actually switch and I'm going to be showing you sort of the power of this IDE by itself. So I'm going to exit out of that and I'm going to open up a Python terminal. I'm going to make it a lot bigger because that's probably hard to see. Hopefully that's readable to everybody. So what is Presolve? Presolve, despite the name, doesn't actually solve problems. Presolve, it's an industry standard name for this sort of algorithm. Presolve is a set of algorithms that are used to manipulate a problem in a way that creates something that's mathematically equivalent but easier to solve. And what I mean by that in practice is most often it's sort of clearing out, it's doing small bits of math or algebra that clear out some redundancies in your problem. So let me give you an example. Let's imagine that I have 3 variables, and they're going to be integer variables. So we'll call them I, J, and K. And I'm typing this live, so forgive any typos, they will happen. And I have a constrained quadratic model where the objective of this constrained quadratic model is to minimize I plus J plus K. So let's take a look at this. So when we take a look at this model, we see something, again, very much like what we were saying before, where you have an objective, which is in this case, which we always try to minimize. So it's to minimize I plus J plus K, subject to, well, I don't have any constraints so far. And it's worth noting that these are integer variables. So those integers are going to take a value somewhere between 0 and this very large number. I don't actually know, thousands, millions, billions. It's a very big number. And on inspection, this problem is sort of obvious. You can see that the minimizing solution is all zeros, but this is meant to be sort of an example. This is deliberately human readable. You can sort of take this by analogy to a different application. Okay, so let's start adding some constraints to this problem. So the first constraint I'm going to add is that constraint I plus J is less than or equal to 5. And I'm going to add another constraint, which is that J is equal to 3. So if we take a look at this model, we can see that those constraints have appeared. My objective is the same, I plus J plus K, but I have some constraints, which is that I plus J are less than or equal to 5, and J is equal to 3. So, fairly classic algebra problem. So up until recently, if you were to submit this problem to the hybrid solver would take it and it would solve it just in this form. It would look at it, it would say, great, these are all constraints, I'm going to work away with it, and I'm going to use all of my techniques to try to solve it. But the runtime of the hybrid solver is directly proportional in a sort of complexity sense to the number of variables and the number of constraints in the model. So if we could remove a few variables or remove a few constraints to simplify this equation a little bit, we could get better performance out of our hybrid solver. And that's exactly what Presolve does. So if I import our Presolver, and we give our model to the Presolver, we go ahead and load some Presolvers and apply them. We can take a look at the resulting model. Oops, that was one of my typos. And when we do that, we can see that it has done what we would expect, which is that it's identified, first off, that this integer j is equal to 3. And it can just go ahead and remove that model. So our objective used to be integer plus integer plus integer, and now it's 3 plus integer plus integer. So one of our variables was removed because we had fixed it. It also then notices that we have this equation, which is j plus I is less than or equal to 5. Well, j is equal to 3. So really what that means is that we have another integer I, which is less than or equal to 2. And so, you'll note this didn't finish solving the problem, but it did remove both constraints and some of the variables. And that makes this problem sort of easier to solve. So in general, Presolve does this sort of thing. It doesn't sort of fully solve problems, but it sort of manipulates this problem to do some of the simplifications, just like you would if you were trying to solve this problem pen and paper. I will mention that, and I should have mentioned off the top, that the reason I'm showing this Presolve in this way is because Presolve is actually just applied by default in the hybrid solver. So when I was running those problems before, the hybrid solver under the hood was using Presolve. But Presolve is also available in Ocean, in those open source tools. And so you can run it sort of locally like this before even submitting the problem to save on network bandwidth, say, or maybe just to understand or add your own Presolve techniques. So most users won't need to do what I just did, but I wanted to kind of peel back the curtain a little bit to show you what this looks like under the hood. So with that, I will return back to the slides one more time. So just to kind of hit some of those points, one of the main benefits of Presolve is that it can be used to reduce the problem size and to make the problem, in some sense, easier to solve by our hybrid solver. It removes unnecessary variables and constraints by doing some sort of small mathematical algebraic substitutions. And then ultimately, this gives you better quality solutions because it makes these problems sort of better to, easier to solve or sort of more accurately representing the actual problem that you want to solve. And finally, this is a really great example of why we use hybrid solvers in the first place. Presolve techniques are, a well-understood advantage of classical systems, and why not use that? Why do we have to limit ourselves to just quantum when we could be using both classical and quantum so you're getting the best of both? And so Presolve is just another example of being able to bring in some of the excellent work that's been done up till this point in classical systems to give benefit to a hybrid system which uses both classical and quantum. So that's the end of the content that I want to be sharing. I will mention that there are many sort of places you can get more information. You can contact D-Wave directly by emailing sales@dwavesys.com. You can check out our launch program. So that's our program for helping you solve practical problems. You can see our set of applications. You can sign up for LEAP. Lots of different things that you can do to to get started with D-Wave or to learn more. And with that, I'll pass it back to Susan.
Great. Thank you so much, Alex. We have a lot of questions that have come in, some of which have been answered. So if you do have questions about the content, please go ahead and put them into the Q&A box while we are still online. We wanted to mention before we got to that our annual Qubits Quantum Conference will be taking place in Miami, January 17th to 19th. We will also be streaming it live, but we are encouraging people to come to Miami. It will really give people an opportunity to speak with our very high quality speakers from around the world. We have people from companies such as MasterCard and Deloitte and many other enterprises who will be speaking. So take a look at qubits.com and you can see the agenda and you can register either for online viewing or to come join us in Miami. We'll also have a lot of great networking events, and there are worse places to be in January than Miami, depending on where you are around the world. So with that, we are going to go ahead and ask some of the questions of Alex that people asked while he was chatting. How many weighted constraints can be added to the model? And another way to ask, what is the trade-off for adding more weighted constraints?
Yeah. So our constraint quadratic models right now, you can submit up to 100,000 constraints, and those constraints can be of any variety. So they could be either weighted or soft constraints, but you have that same 100,000 budget either way. So 100,000 weighted constraints or 100,000 unweighted constraints, or some mixture of both, 50-50, or any mixture. In terms of the trade-off, I would say that, if you want, I mean, the first answer is kind of maybe a bit tautological, but it's just to say that if you want your constraint to be able to be violated, you should use a weighted constraint. If you know that your constraint shouldn't be violated, you should use a hard constraint. Hard constraints are, they're treated a little bit differently under the hood. So, hard constraints are sort of by definition, we try harder to satisfy them. And so, yeah, I would say just make sure I wouldn't overuse soft constraints unless you need them, is how I would describe it.
Okay. Is there a way to get all the solutions ordered by their cost, including infeasible ones?
Yes. The solution set returned to you by the hybrid solver and available in Ocean will have all the solutions returned by the hybrid solver. Each of them will have whether they are feasible or not and their cost as the energy.
Okay. Are the weights out of 100? What is the max min values that can be used?
You use floating point numbers. The minimum value is 0, so you can't have negative weights at the moment. But you can use sort of any number. I will say that, as in most things in computer science, when you're using floating point numbers, I wouldn't use like truly enormous numbers, like in the quadrillions or whatever. But other than that, everything should work fine.
Okay. Do the solvers take as input vectors, matrices instead of single values as variables?
We have, I'm not 100% sure I fully understand the question, but I would say that our variables are either binary, integer, categoricals, which we call discrete. So that is to say like red, blue, yellow, green, or continuous. So they can take multiple values. So that answers maybe the variables part. In terms of like, can you represent your problem with a matrix or vectors? Then yes, we sort of use those to represent the biases on those variables.
Okay, just for clarification, is the CQM also doing Presolve when it is given a problem, or does one have to run Presolve for this?
So the CQM solver by default runs Presolve, and then you could also run it locally if you wanted. If maybe you wanted to save on network bandwidth or shrink the size of your problem before submission.
Okay, is it correct that Presolve works completely classically, i.e. without any execution on the quantum computer?
Yes. In principle, there is part of the reason we put Presolve in open source is because there are ways that you could hybridize that, and we wanted, we're interested in that, and we wanted to give that to the community to also, play around with. So, but at the moment, it's purely class.
Okay, let's see. We have our panelists answering some questions here. In the pre-solver context, what is the problem that we will submit to the solver? The simplified one, and what kind of result do we get?
Yeah, yeah, and I should have probably made this clearer, so I'll just make sure I really foot stomp this, which is that you can submit your problem just like you were before, and the solver will now make use of Presolve server side. So you don't need to make any changes. You can run it locally and then submit the reduced problem, the one that was sort of created by the Presolve to the system as well. The system will rerun Presolve and then it won't find anything, but luckily it's very fast in that case, and then carry on. So you have sort of the option of running it locally if you like.
Okay. How does it map the problem from CQM to BQM before sending it to the solver, but after converting it to BQM, can you add terms to the model?
So you could take so in terms of, could you add terms to the model? You could take if you ran Presolve locally, you could Presolve your problem, take the reduced problem and then manipulate that. You could add terms back in or make changes to it. That might actually be a very smart thing to do in some cases, if you sort of have some special knowledge of your problem post Presolve. In terms of how it relates it to the BQM, I will say that our hybrid solver sort of the whole reason we use a hybrid solver is because it can use the quantum computer and classical computers to solve the problem in its native form. So there isn't sort of a direct to BQM translation that happens in our hybrid solver. We do have some abilities to translate CQMs into BQMs in Ocean. We don't generally recommend them because when you're working with heuristics, sort of native representation is really important, which is why we have a CQM solver in the first place. So it's almost always better to let the CQM solver sort of manage the problem and handle the submission to the QPU, unless you sort of know something really specific about your problem class that allows you to get around that. And that's exactly the kind of thing that you would work on in a launch program with our professional services group, is sort of working through that balance. It can be done, you can be done on your own, but it's generally easier to have experts as well.
Okay, I will just take a couple more questions, and I hope I don't butcher this one entirely. Can CQM accommodate non-convex optimization problems over C caret N, and will Presolve work with complex numbers? And maybe that means something to you, but unfortunately.
Yeah, it does. So the CQM solver is a quadratic solver. So we don't take like objectives with sine terms or log terms or whatever. It's quadratic, but it is non-convex. So you can send non-convex quadratic expressions to the system.
Okay, let's see. All right, let's make this the last question of the day here. There are public guidelines to improve CQM models or solver configurations that, when the number of variables of the problem instance grows, produce only infeasible results. The Presolver may help in these situations.
Sorry, could you say the question again?
Sure. Maybe the question is, are there public guidelines to improve CQM models or solver configurations that, when the number of variables of the problem instance grows, produce only infeasible results? And would the Presolver help in these situations?
So Presolver doesn't necessarily help in the infeasible case. That's sort of really where the weighted constraints provide their value, is when you have a problem, instead of constraints that can't all be satisfied, you want to sort of weight them relative to each other, because otherwise the solver is just going to try to satisfy them all, and it can kind of, and that's not an efficient way to solve the problem. In terms of there being guidelines, we have some guidelines in our documentations to talk about how to sort of scale your problems in various ways. In general, although this is an incredible generalization, so there are many cases counter, making your problems larger actually makes them sort of easier to satisfy. You're often expanding the feasible space, but not always. There are definitely exceptions to that. So.
Okay, well, I think with that, we're at the end of our time here. Thank you very much, Alex, and thanks to everyone who attended. Again, we've recorded this, and you can find it on the D-Wave YouTube channel the next day or so if you'd like to go back and watch it again. And please pass it along, and please, again, take a look at qubits.com. I would love to see all of you either in Miami or online for our annual conference. Thank you.
Thanks, everyone.
Bye-bye.